Section 3.2 exercises. Problem 1. Is it true or false that the exponents on the variables in a polynomial function must be non-negative integers? This is absolutely true. When we say non-negative, we mean the set of integers that begin at 0. That's why we say non-negative, and they include then all the counting numbers like that forever. So we just can't have negative integer exponents. Problem 2. Is it true or false that the graph of a polynomial function may have a sharp corner? This is absolutely false. We need that the graphs are always smooth, so they would be fun to drive, and continuous, meaning non-broken, and they must have rounded turns. So much like a roller coaster or a road that's fun to drive. Problem 3. Use a leading coefficient test to determine the end behavior. Okay, here I refer to this as the dominant term, which is the term of the highest exponent in the entire polynomial, and here our lead or dominant term is x to the 4th. What we wish to ask is, as x becomes very, very large, what happens to that dominant term? Well, a very large number raised to a 4th power will also get very, very large. That means that the graph will end up going up to the right. We also need to ask what happens as x becomes very large in the negative direction. And because x has a power that is even, x to the 4th will have the same behavior as before. It will also grow in a positive way and become large. So the graph will be up left. By writing up right and up left, we mean that on the graph, as we go way out on the x-axis, the function will rise up, and as we go far out in the negative x direction, the graph will eventually be moving in the upward direction like that. Let's do the same thing, but for a different function. Here the lead term is a little more difficult to see. We could multiply out the entire function, but we don't need to. We simply take each factor and look at the highest degree term that occurs in each of these factors and multiply that together using rules of exponents, getting 2x to the 5th power. Now we apply the same reasoning as before. What happens as x approaches a very large number and grows? What happens to 2x to the 5th? 2x to the 5th will also grow and can become very large, so the graph will be up to the right. However, as x gets very large in the negative direction, because we have an odd power on the value of x, 2x to the 5th will then be a negative number, and it will continue to decrease and become larger in the negative direction. So that'll be down on the left. So that means that the graph would have a view up on the right and down on the left, and that would be the end behavior there. Problem number 4. We were asked to find the zeros of the following function. Finding the zeros of a function means to find the x-intercepts. So to do this, to find the x-intercepts, we have to make the function equal to 0. So we will take the function x cubed plus 2x squared minus 4x minus 8, set it equal to 0, and to do that we have to factor. And this is a little tricky to factor. If we group the first two terms together and factor out common factor of x squared, we're left with x plus 2. And if we group the next two terms, we have a common factor of negative 4. We can take that out, and that also leaves us with the second factor of x plus 2. Now, continue to factor. You have a common factor of x plus 2 in each of these. Take that out, leaving us with x squared minus 4 equal to 0. The only way a product can be 0 is if each of the pieces, each of the factors are 0. So this would give us one x-intercept at -2, 0. And the other factor, x squared minus 4, can be 0 when x squared is 4, or when x is plus or minus 2. So in this case, we have a repetition of zeros, and there are only two answers, -2, 0, and +2, 0. That's where the function will cross the x-axis. Problem 5. Find the zeros of the given function and give the multiplicity, meaning how many times those zeros occur. So we'll take the function as it is, and we'll set that equal to 0 and attempt to find the x-intercepts. Our function's already factored, so we need to work on the solution. We could divide both sides by -4, and that will eliminate the -4 multiplier in front. Now we repeat the process as above, setting each factor equal to 0. Well, x plus 1/2 squared means x plus 1/2 times x plus 1/2. So I'm going to factor that twice. That will give us the 0 of -1/2, but it occurs 2 times, and that means multiplicity 2. We'll take our second factor, x minus 5, to the third power. That means x minus 5 3 times. And that gives us 1, 0, x equals 5, and it occurs 3 times, so that's multiplicity 3. With odd multiplicity, the graph will cross the x-axis. With even multiplicity, the graph will touch the x-axis and bounce off the x-axis. Problem 6. Show that the given polynomial has a real 0 between -3 and -2. To do that, we require that the y value at -3 and the y value at -2 have opposite signs. This would then put one y coordinate above the axis and one y coordinate below the axis and guarantee that the function, which is polynomial, being continuous, must cross the axis between those 2 points. So we'll find the y value at -3, substituting -3 in for x, giving us 3 times -3 cubed minus 10 times -3 plus 9. And that will give us 3 times -27 plus 30 plus 9, 39. And that result will be -42. So that is below the x-axis. We hope that the next y value is above the x-axis to guarantee it has a 0 in between. The y value at -2, substituting that into the function, plus 9, will give us 3 times -8 plus 20 plus 9 plus 29, which results in 5. Positive number, so that is above the x-axis. And again, since a polynomial graph is continuous, it must cross the x-axis between the value of -3 and -2 for x. Problem 7. If a polynomial function f of degree 5, what is the greatest number of turning points on its graph? A polynomial function of degree n has, and this is at most, doesn't mean it has this many, it means at most n minus 1 turns. So here for us, we have n being degree 5, so 5 minus 1 is 4. At most, 4 turns or changes of direction can occur. Problem number 8. Use a multiple step strategy to graph the cubic function f of x. Okay, to do this, we'll first look at the lead term and determine the end behavior. Lead term is x cubed, and as x is very large and positive, x cubed will also be very large and positive, so the graph will be up on the right. Also, as x gets very large in the negative direction, since our exponent is negative, x cubed will decrease in the negative direction and become very, very large. So that means that it will be down on the left. So the graph is going to have up, right, and down, left appearance on the far left and right portions of the y-axis. Let's also find the x-intercepts. To find the x-intercept, simply set the function x cubed minus 3x squared equal to 0 and factor that. Here we have a common factor of x squared, and taking out that common factor, we have left x minus 3. Setting both equal to 0 gives us x squared equal to 0 and x minus 3 equal to 0. Since x squared can be factored yet again, we get x equals 0 twice. So that is multiplicity 2, and the graph will bounce off the x-axis there at 0, 0. Then the second x-intercept occurs when x is equal to 3. Since that root appeared one time, the graph will then cross the x-axis at that x-intercept of 3, 0. We can also find the y-intercept. Very easy to do. Simply compute f of 0, putting 0 in place of x in the function, and you get 0. So we already have this as an x-intercept. So no new information obtained there. We can look at the max number of turns. That sometimes is a help. And degree 3, so minus 1, 2. At most, 2 turns for this function. And let's see, symmetry. Well, we have a mix of even and odd powers. So we will have no symmetry. There's a formal test that we can apply to that, but we'll say it briefly like that. Let's transfer this information on coordinate system and see where it brings us. Coordinate system, so we have the origin as an x and y intercept. It will bounce off that point. We have 3, 0 on the x-axis as an intercept, and we also have far right behavior and far left behavior, and we also have max turns to be 2. This will force the graph to look like this. And one of the questions is approximately where is that minimum occurring, so we could plot an extra point. And this is just to improve accuracy. To do that, we have an x-intercept of 0 and 3, so an ideal point to plot would be when x is 2. And if we do that, we get y being negative 4. And that will then transfer this point to negative 4 here, and it will make the graph more accurate, forcing the curve to be tighter, have a lower minimum, but still retain all the rest of the characteristics it had before. And that concludes section 3.2 exercises.